In this video, I'm going to go through uh, the set of smart notes on cross-sectional areas. I know I kind of left you on your own to see what you could come up with in terms of figuring this stuff out, but I'm going to go through the smart lesson just like I would if it was a regular classroom setting, minus the feedback from students. All right, so as we've already studied, if we're doing volume, we've done volume with washers and discs, and in both of those scenarios, it was just a matter of taking a region and slicing it up into different shapes. Whether we had, so earlier on we did, say, washers. They were so thick. We'd stack a bunch of those washers on top of each other and basically sum the areas, because when you did the volume, it was the area of this piece times the thickness, and the thickness was always just dx or dy. So it was basically area of the face times the thickness, and then we summed them between our start and our end. So this is the exact same thing. The only difference is, rather than the shapes always being circles, like they have been so far, discs or washers, we did do the shell method as well, but still you were dealing with a circular situation. In these questions, the only difference is the shapes are not circles. And just depending on what the shape is, will dictate what formula we use to get the volume of the object. So if you look at this picture here, so you can see they just have some kind of a strange irregular shape. They cut this one cross section out here that you can see, but if they were to cut another cross section down here, it'd be the exact same shape as this. Only difference is it would be smaller. So any slice you make of that object would be that same shape, just a different size. So they would get the area of each of these. Each one would be dx in thickness. So to get the volume, they would simply integrate the area of the face, which you see up here. So integrate from A to B, that's the start and the end, area of the face times the thickness of the cross sections, which is a slice of the x-axis, so we can refer to that as dx. So here's an analogy of a loaf of bread. So it's kind of that idea. Every slice is kind of the same shape. You get the area of each one. So imagine that to get the volume of that slice of bread or that loaf of bread, you cut these slices infinitely thin, and you basically get the area of each slice and then added them all together. That would give you the volume of the loaf of bread. So this is just a couple more images. So this one talks about, you've got a solid, has a circular base of radius 1. So the picture over here shows that pretty well. So that. Now I know sometimes people say, where did this come from? We're supposed to know from our studies that if you have a circle and you wanted to get the equation of any circle, it's always x squared plus y squared equals the radius squared. That's the general equation for any circle. So this set of circles, center the radius, or center the origin, which is there, a radius of 1. So its equation was x squared plus y squared had to equal 1. If that had said the radius was 4, this would have been x squared plus y squared equals 16. And then simply they just rearranged this formula to get y equals that. So then, if you looked at your cross sections, every cross section says is an equilateral triangle. So if I take this object here, now there's a nice computer generated image of it. My graphs and pictures aren't going to look that nice. So here's the object right here. That's the base of it. So this cross section, if you can imagine, coming out of the screen right towards you would be a triangle. Now I'm going to try and draw that as best I can with this stylus. So it's going to come out. And this would come out. Now this is just one of these triangles. And what it said is every time you draw one of these, so I'll just draw another one. So there'd be one over here too. So you could draw, oops, so if you drew that, and then that would be another one. And then what they said is that every time you do this, the triangles are equilateral, meaning the side lengths are all the same. Like so. So what we're going to do is get the area of each one of these triangles, and then we're going to sum the areas and do that through integration. So I'm just going to draw one of these triangles so you can see it. So let's take that one that I drew up here. So this triangle right here, if I just draw it out, still not very good with these lines yet. Try that again. So if I try that triangle, it will look like, let's see here. So this will come down, out, out. Triangle. This side and this side, they're all the same. Now, I want to get a measurement for at least one of these sides. Well, this side here, doesn't matter where I draw the triangle, the distance from here to here will be the y value on the circle. Well, the y value on the circle is always this function. So from here to here would be the square root of 1 minus x squared, this piece. Well, so would this piece down here because it's symmetric, so it's going to be the exact same thing. So this total distance from here to here would be this plus this, which makes this side 2 square root 1 minus x squared. Well, then all the sides are that. And because it's equilateral, that means that all the angles are also the same. So 60, 60, and 60. This angle is 60. This angle is 60. Well, I need to get the area of this triangle. So there are two formulas you should be familiar with to get the areas of the triangle. Sometimes we forget about one of them. Everyone remembers this one. They say, oh, I'm going to do the area of the triangle. Its area is half the base times the height. And you're right. But to use that formula, it's most beneficial to make sure you know the base and the height. If you looked at this diagram I have here, if you say this is the base, well, one of these slanted sides here are not the height. The height would be this perpendicular distance here. So there's a better formula to use in this situation, which would be area is 1/2 AB sine of theta. And now if you remember how this one works, you need to have two sides, A and B. That's what the A and B are, any two sides in the triangle. And then you have to have the angle that's between them. They call it the contained angle, that one in between. So if I knew that, then I could get the area of this triangle. So the area of this triangle is 1/2. Well, A and B are the same, so it's going to be 2 radical 1 minus x squared, that's AB, and then the sine of the angle between them, which is 60. Now imagine you're sitting at university next year and you didn't have a calculator. So, well, how am I going to get the sine of 60? Well, you got to remember this diagram. So we had our triangle, look like that. That's 60. So we get 2. This is 30. Across from 30 is always 1. And across from 60 was your radical 3. So the sine of 60 is radical 3 over 2. Go down here. So the area is 1/2. Square this. I'm going to get 4 onto 1 minus x, because when you square the square root, it just gets rid of the radical. And the sine of 60 is radical 3 over 2. So we just clean this mess up. So half of 4 is 2. That 2 is going to cross that 2 out. So when all is said and done, the area of my triangle is radical 3 multiplied by 1 minus x. So that's the area of one of the cross sections. So to get the volume, you sum the areas from start to finish. So if I look at the, back up to our diagram, so I get two options here. I can start in the middle and go 0 to, remember this point, because the radius is 1, this is the ordered pair 1 comma 0. So I could integrate from 0 to 1 and double my answer, or I could integrate from -1 all the way over to 1. And the reason I can do 0 to 1 and double is because this side over here is the exact same as this side. And it's always nice to have 0 as one of our substitutions. So I think I'll do it that way. So here would be the integral. That would give us the volume we're looking for. All right, so it's going to be the integral from 0 to 1. I'm going to double it. And it's the area of the cross sections, which are all radical 3 times 1 minus x, times the thickness of each cross section, which in this case would just be dx. So if I want to continue with that integral. Let's have a look here. So we're going, anytime I have constants, I always try and get those all gathered together and moved out front. So I've got radical 3 times 2. So out front here, I'm going to have 2 radical 3, integrate from 0 to 1, 1 minus x dx. So let's do the integral of this. 2 radical 3 will just stay there. The integral of the number 1 is just x. The integral of x is x squared over 2. And we're going to calculate that between the bounds of 0 and 1. All right, so now we're going to substitute our values for x. So I've got 2 radical 3, bracket. So substitute 1 minus 1 over 2. There's your upper bound. So when I put 0 and 0 in here, that's going to make that an easy substitution. So that's 0. 1 minus a half is a half. So I've got 2 root 3 times 1 half. She'll cross that out. And this is equal to root 3. So the area of this 3D object is, sorry, not the area, the volume of this 3D object, not area, that would be volume. The volume would be root 3 cubic units. So I went through this one yesterday. I didn't show all the work, but hopefully that example that I just did would help you with that one. Let's look at this one. I'm not going to do all of these, but I will do a couple of the ones at the bottom, just because we haven't done anything with circles yet. So let's take this one, and we'll start with we'll do part E and part F. So in this one, first thing I'm going to need to do is get a picture of what these graphs look like. So I've got two functions, 8 minus x squared and x squared. So when I go to draw that, I want to know where they cross each other. So I'm going to figure out what the point of intersection is. So when I do that, I'm just going to move this over here. I've got 8 minus 2x squared equals 0. Common, I can divide everything by 2. So now I got 4 minus x squared equals 0. Difference of squares. 2 subtract x. 2 plus x equals 0. So the points of intersection are plus or minus 2. All right, so if I go to my graph, so at this one, if we just go up here, now this, we should know that's a parabola opening down, and the vertex has moved up to 8. This is just your standard parabola with its vertex, the origin, open up. So let's draw what we think this base looks like. So I've got 0, 0. I've got, so if x is 2, so I'm going to need 2 comma 4. So let's put 8 up here. There's 8. 4 would be here somewhere. Let's say 2 is here. Minus 2 is here. Now, let's see, I'll make a drawing these with this thing. So this is my regular old parabola. At this point, and this point of intersection. The other one opens down, so I'll try and draw that one as best I can here. So this one's going to come up through here and down through there. All right, getting better. So this one is y equals x squared, and this one is y equals 8 minus x squared. So this time it says every cross, so I'm doing part E. Part E said every cross section, when you draw it, so I'll just pick one. Here's a cross section. Fine. Try that again. Here's a cross section. There's semicircles, so that's the bottom of the object. So then it's going to come up and be a half circle like this. Well, this distance down here from here to here would be the diameter of that whole circle. So if I just draw kind of a bigger image of what we've got this semicircle like this. The distance from there to there, go to your graph, it's upper minus lower. So the upper is the parabola 8 minus x squared, and the lower is this one. So this side right here is upper 8 minus x squared minus the lower, which would be the same thing as 8 minus 2x squared. That's the length of this side. Well, the area of a circle is pi r squared. I have half circles, so there's the area of each one of these cross sections, 1/2 pi r squared. So let's get the area of this particular cross section. So area will be 1/2 pi. So the radius, now you got to remember, this is the diameter. It's all the way across the circle. So the radius is half of that. So it's going to be 8 minus 2x squared over 2 squared. Now let's clean this up as best we can. We could divide both of these by 2 and say we've got 1/2 pi 4 minus x squared squared. I think we'll just leave it like that for now. We could expand it out. Sometimes expanding it out now would help. Sometimes it doesn't. We'll see which is our best option here. All right, so we're going to write an integral now to give us the volume. So remember, the volume is the sum of the cross-sectional areas. And what I've just calculated there, that's a cross-sectional area. So let's go. Volume would equal the integral. Up to your diagram here, notice where we're going to start these cross-sections. We're going to start them at -2. We're going to stack them side by side until we get to here, which is +2. So the bounds, now this one, it would be symmetric. So we could go, if we wanted to, we could go 0 to 2 and double it. And that would give us the same thing over here. Why don't we do that again, just to make our calculation easier? So we'll go 0 to 2 and double it. So lower bound of 0, upper bound of 2. We're going to double the answer because that's only half the object. And it would be pi times 1/2. I'm just kind of rewriting this here. 4 minus x squared squared. So 1/2 pi radius squared. And now I need the thickness, which is dx. So this integral is going to give me the volume of that 3D object we create up above. Okay, so let's tidy this up. Myself some more room here to work. Okay, so this, let's see what we've got here now. So we're going to go volume equals, let's take, well, I got 1/2 and a 2 here. So those are going to wipe each other out. So I'm going to just have a pi out front. 0 to 2. Now, I'm going to have to expand this out because if I wanted to do it as a chain rule, I'd need to have a dx or du beside it here, and the du would have a 2x, which I don't have. So I'm going to actually expand this out with my 3-step rules. It's going to be square the first, multiply these two and double, and then square the last one. Still have our dx. So our volume is going to be pi. We're going to do the antiderivative or the integral. So 16x minus 8/3 x cubed plus x to the 5th over 5. And we're going to integrate that from 0 to 2. All right, here we go. So our volume is going to equal pi times, I'm going to substitute 2 now, so it's going to be 16 times 2, 32. 2 cubed is 8. 8 times 8 is 64 over 3. 2 to the 5th is 32 over 5. So that's the upper bound. Substitute it. And again, 0. This is why I cut it in half. It makes this substitution a lot easier. When you put 0 in here for x, nice and easy, everything's going to be 0. Okay, so now we are going to keep going here. We're almost there. So I'm going to have pi 3 and 5. So I need a common denominator of 15. Yikes, 32 times 15. Calculator handy. 1 sec. 32 times 480. So this is 480 over 15 minus, we're going to multiply 64 by 5. That would be 320 over 15. And then 32 times 3, that'll be 96. And we will end up with a total of, so 480 plus 96, 256 pi over 13. 256 pi over 15 cubic units. I don't know if that reduces or not, but I don't have my calculator in front of me. I just use doing it on my phone, so if that reduces, you would reduce it. Okay, so that is semicircles. I'm going to do it one more time. I'll do quarter circles. So I'm going to take the same question. Let's see if I can clone this. New page. And we will do it again. So this time we're on F. We're going to do it as quarter circles. We're going to have the same graph. I'll just quickly draw the graph again. So the graph's going to look just roughly like this. So it's going to go up, up. This time, when I draw a cross section, let's say I draw it here. It's not a semicircle, it's a quarter circle. So this would come up like this and go down like that. You have a right angle here, and this would be a quarter of a circle. So this time, the piece across the bottom here is not the diameter, it is actually the radius. And this part up here is going to be the same distance. It's a radius as well, but yeah, it doesn't really matter. Okay, so I need the volume of that shape. Well, let's draw it out here a little bit bigger. So I need this distance, which will be the radius. Well, that distance from there to there, we just did it in the last one. It's upper minus lower. So it's 8 minus x squared minus an x squared. So that makes this side 8 minus 2x squared. That's the radius. So I want the area of this shape. So the area of this shape is a quarter of a circle. So 1/4 pi r squared. Like so. Well, we're going to go volume then. Volume will be the integral. So we'll do it the same as the last time. We'll go from 0 over to 2, and we'll double that. 1/4 of pi times 8 minus 2x squared dx. Okay, clean it up before we get going. So I've got 2 times 1/4, that's going to be 1/2, and pi, that'll come out front as a constant. 0 to 2, 8 minus 2x squared. Oh, I should actually expand that out. Let's just save us another line. So I'm going to actually expand this out. So square the first, 64. I'm multiplying double, so 8 times 2 is 16. That'll make the middle 32x squared. Square the last one, 4x to the 4th, and dx. So the volume will equal 1/2 of pi. Take the integral, 64x minus 32 over 3x cubed plus 4/5 x to the 5th. And then we're going to integrate that, not integrate, but evaluate from 0 to 2. And I'm not going to show all that out, but you guys could substitute 2 for x, substitute 0, subtract, multiply by pi, and you get your answer in cubic units. Okay, so hopefully these examples will clear up any confusion you were having. And again, if you're still stuck, so there's a few more examples to follow here in the smart slides. I think most of them have the answers there beside them, so if you could work through those on your own and see if you're kind of getting the hang of things, that would be a good idea.